finish
All
by
right.
one. I have to finish by one, right?
Yeah. Okay, welcome to the Science Library at the University of Oslo. And today we're very excited to hear about active galaxies and supermassive black holes, which are super fascinating objects in the universe. And we are excited to have Professor Dhruba Saikia here to tell us about it. He has been doing important research in this field for many years and also about the radio universe and a lot of interesting things. So we're very happy to have you here. Welcome, Professor Dhruba Saikia.
Thank you. Okay. First, let me thank the organizers, particularly the library, and Rubinu, who initiated the whole process, for inviting me here. It's my first visit to Oslo, and it's a real joy to be here. Thank you very much. So we have to finish by 1 o'clock, so I'll give you a brief overview, and as well as some recent results on active galaxies and supermassive black holes. And if you have questions in between, you can raise your hand. But if it's a long answer, I'll wait till the end, okay? Right. Now, before getting into active galaxies, let's just, because I was told it was for a very mixed audience, let's just take an overview of what galaxies are, our own galaxy a little bit, and then we'll get into active galaxies and supermassive black holes. If I'm speaking too fast, just raise your, indicate to me that I should slow down, and I will slow down a little bit, all right? This is one of the very recent maps done by a major survey called the Dark Energy Spectroscopic Instrument. This is the 4-meter telescope located at Kitt Peak called the Mile Telescope. And it was a survey to actually look at millions and millions of galaxies, to look at our universe, because one of the important discoveries of our universe is that it is not only expanding, but is also accelerating. Is the acceleration uniform or not? Or how is it changing with cosmic epoch? Was one of the major goals of this survey. They have imaged about 47 million galaxies. They've taken spectra of these objects, and it has been a phenomenal success because they were initially hoping to image just about 34 million of them, but the instrument works efficiently. They have got 47 million of them. Now, each dot over here is a galaxy, and the further away from the center they are, the more distant the galaxy is away from us. Galaxies are the basic building blocks of the universe. You might think that they only consist of stars. They consist of stars, the medium between the stars called the interstellar medium. It has magnetic fields, high-energy particles embedded in them, and the whole galaxy is embedded in what is called a dark matter halo, which makes up about 23% or so of our universe. Dark matter, because we can't see it, it doesn't emit light, but the effect of its gravity is what one feels in our galaxy as well as in the cosmos as a whole. These are some of the furthest galaxies which have been imaged. JWST, the James Webb Space Telescope, has gone even further. The most distant ones, which you see over here, are about 11 billion light years away. As you know, our universe is about 13.8 billion years or so. Now, galaxies come in a wide variety of shapes and colors. Shapes, they could be elliptical, like an egg-shaped or a bun shape projected onto the sky plane, or it has beautiful spiral arms. We'll see one or two examples in a short while. And colors depending upon how old or young they are. Because if it's a young galaxy where a lot of stars are forming, then you'll find a lot of young stars. And young stars are whitish or bluish in color. And that is because they are of the temperature of these stars. And why are they young? Because they don't live very long. The massive stars, they live a short lifetime, few million years, and then they die off. Whereas the older stars, like our sun, for example, or even cooler stars than that, they would be reddish in color, and they will live for billions of years. A sun has a lifetime of about 10 billion years or so. So the older galaxies are reddish in color, younger galaxies are bluish in color, and they come in a wide variety of shapes, as you've seen over here. They're arranged in a way where Edwin Hubble, who first tried to classify galaxies, classified in what is called as the Hubble tuning fork diagram. But what is shown over here are the major galaxies, big galaxies. The universe is full of smaller galaxies called dwarf galaxies, much smaller than our galaxy itself, a small fraction of it. Our galaxy may have about 10 to the power of 11 or 12 stars. These galaxies may have about 10 to the power of 6, 7 stars. Okay, and there are low surface brightness galaxies, but we'll not get into too much of those details over here. This is an image of our galaxy. Taken with an optical picture, you can see a lot of dark spots over there. The dark spots are there because there is a lot of gas and dust between the stars, which absorb the light. So if you look towards the center of our galaxy, you really can't see the center at optical wavelengths, even with very powerful telescopes. Extremely powerful ones, you may be able to see a bit of it, but because the short wavelength radiation, the optical light gets scattered by the dust and the gas, which permeates the medium between the stars. If you look at it longer wavelengths, for example, fog lights, which are orangish or yellowish in color, or the sun when it sets, it's orangish in color. These are longer wavelength light comes through. So if you look at our own galaxy in infrared light, this is what you would see. The dark spots have all disappeared. And the dark spots have all disappeared, and what you see is a uniform distribution, generally of slightly older stars. The circle which you see over here, this is called the bulge of the galaxy. We'll look at that in a little more while. But you can ask yourself, I'm talking about stars, I'm talking about the interstellar medium of galaxies, and you can ask yourself, what is the fraction of volume in our own galaxy, for example, which is occupied by the stars? That's sort of a pertinent question to ask. You look up at the sky on dark night and you'll see thousands of stars. But what fraction of the volume does it actually contribute? And we'll just do a little sum over here just to illustrate that if you look at, for example, the size of our sun, we know what the diameter is, or we know what the radius is, so we can calculate the volume. We also know what the nearest star is, Proxima Centauri, and we can calculate what is the volume, assuming it to be a sphere. This is a very simplistic back-of-the-envelope kind of calculation, and you'll find that it is in 1 part in 10 to the power of 24 or so. To give you an idea what that means, that 1 part in 10 to the power of 4, that if you had a small grain of sand, which is, say, a millimeter cubed in diameter, then the nearest star would be, then the other nearest star would be about 100 kilometers away. So I've written down some of the nearby Hamar, Tonsberg, Halden, which is about 100 kilometers away from Oslo over here. So if you have a grain of sand over here, the next grain of sand would be 100 kilometers away. But this is an average value in the neighborhood of the sun. If you go to the center of our own galaxy, it'll be much closer and much more compact, and than the number which I've given you over here. Now, if you look at our own galaxy, this is a schematic illustration of it. This is what is known as the bulge of the galaxy. Here, the motions of the stars are largely random. And if you could actually go outside the galaxy and look what it looks like, you'll see these beautiful spiral arms. We are about 24,000 light years away from the center. We are not in any specific position or preferred position in our galaxy. It's an ordinary star in an ordinary location in a galaxy, in a planetary system where of which Earth is one of it, in which we all live. So these are the kind of scales in light years which is given over here. This is the Monty Python sort of song, the British humor group over there. So this bulge is sort of important in terms of our understanding of black holes, because the properties of this bulge seem to be intimately related to the kind of supermassive black holes which reside generally in the centers of galaxies. So we'll come to supermassive black holes in a moment right now. For example, this is let me see if I can click it again. Okay, it's not moving. Okay, let me see if I can click this, if it moves. Okay, it's moving. So you can see that you want to know the mass of the black hole. How massive is it? And this was an experiment which was done by 2 groups, and they had got a Nobel Prize in physics for it some years ago. And what you do is you're able to pick up light from stars which are very close to the center of our galaxy. And you keep monitoring this position of this star year after year after year, or month after month after month, and trace its orbit. And then you apply what are known as Kepler's laws of motion. Physics students will be very familiar with it. Because the object in the center is very massive, you'll have to apply general relativistic effects as well. But the basic idea is very similar, that you determine the motion of the objects, just like measuring the mass of the sun. And when you do that, you come across a mass which is about a few million times more than the mass of the sun. So 4.3 into 10 to the power of 6 times the mass of the sun. The mass of the sun is a few times 10 to the power of 33 grams. So you can see that there's a huge, massive object which is sitting in the center of our own galaxy. And this particular orbit is what the star was called SO2. It completes one particular orbit, and it goes very close to the center of the galaxy, which hosts the black hole. So you may ask yourself the question that how do you know it's a black hole? How do you know that there is not even 10 to the power of 6 million stars over there just compact compacted over there. If you had 10 million stars in a compact region over here, you can work out a profile of what those distribution would look like, because they would basically be interacting by gravity. But once a star gets very close to it, you know that is not the case, because the star would have rammed into other stars. What I'm trying to illustrate in this particular plot over here, our galaxy actually has a supermassive black hole, but it's a relatively small supermassive black hole. Anything over 1 million solar masses is referred to as supermassive. We have smaller mass black holes as well. For example, dwarf galaxies have 10 to the power of 4 or 10 to the power of 5 times the mass of the sun, and these are referred to as intermediate mass black holes. Now, the more massive the bulge is, the more massive the galaxy, the supermassive black hole is. So the evolution of the galaxy itself is intimately tied to how the black hole grows. So we'll come back to this theme a little later, but it's something which is important to bear in mind. It's a very important relationship which is found by Megarian and collaborators, and referred to as the Megarian relationship. And these are actual measurements of lots of galaxies over here. Okay, so remember that the bulge is not the whole mass of the galaxy which matters; it's the bulge which matters. And the more massive the bulge is, the more massive the galaxy is. Okay, and the more massive the bulge is, then the stars are also moving about more rapidly. So you can plot it against the velocity dispersion of these objects, or you can go and infer the mass of the object or the velocity dispersion as well. Now, a very recent discovery, this is what I thought I would highlight over here. This is just from this month, reported 19th August 2026, came out in Nature, that they found an object which is even closer to the supermassive black hole. And this is the object over here, which has a period of about only 8.7 years. The other was more like 16 years or so, and it goes very, very close to the black hole. The closest distance is what is referred to as the Schwarzschild radius. Every massive object has what is referred to as the Schwarzschild radius, which depends entirely on the mass of the object. And it is, for black holes, it is a region within which, if you go, light will even not escape from it. And this object is hurtling around at a velocity of about 25,000 kilometers per second. So this is an extremely valuable sort of result which has just come out recently. And of course, in the study of black holes, two of the images which have been directly imaged with radio telescopes is shown over here. One is of a nearby galaxy called Messier 87, and the other one is the center of our own galaxy. The more massive the object is, the larger the Schwarzschild radius is. For example, this black region over here would mark the inner part where there are no photons. Photons fall directly into the black hole. This one has a much larger black hole, but is more distant. Our galaxy is a much smaller black hole, but it is much nearer. Because it is nearer, the angular dimensions look similar. And from the Schwarzschild black holes, from the size of these images, you can also determine the mass of the black hole, because you know where the Schwarzschild radius is, and that essentially depends only on the mass of the object. And for the Galaxy M87, it is about 6.5 billion solar masses. So you can see we have gone 1,000 times larger in terms of mass in a nearby galaxy called M87, which is one of the very luminous nearby active galaxies, which we'll talk a little bit more detail in a very short while. Okay, now I should mention about these two images, because to image this is a huge challenge, because you need high angular resolution. You're going right near the black hole. And the more distant it is, the more of a challenge it is. And so astronomers got together and say, we want to map the event horizon of a black hole, and they set up a consortium of telescopes at different locations of the Earth to combine all the signals to get this high angular resolution. What is the kind of angular resolution we are talking about? We are talking about at sort of tens of micro arc second level. How to compare it with that? For example, the human eye is about an arc minute or so. So you're not only talking about arc minute to arc second to milli-arc second, you're talking about micro arc second. To give a physical idea what that means, if you took an apple and put it on the moon, you should be able to resolve it with the kind of telescopes which we have. For students of physics, the angular resolution is lambda divided by the diameter. So the smaller the lambda is, the better the resolution you can get. Larger the d, the better the resolution. So you go to millimeter wave region of the spectrum where these interferometry techniques are well established in the radio regime. You go to millimeter wave and get as long an antenna, the baseline as you can get, right from the South Pole to whatever telescopes in Europe as well as the US. They were all combined together to make these images. So these are the kinds of supermassive objects for which we have direct observational evidence for it. Now, just a word or two about active galaxies. So when I talk about our galaxy or Andromeda Nebula, say the Andromeda Galaxy, often we have referred to them as normal galaxies. So what do we mean by normal galaxy? That the major understanding of a galaxy can be understood in terms of the passive evolution of stars. Stars are continuously born, they continuously die. As I said, more massive stars have a shorter lifetime compared to the less massive stars. But if I can understand a galaxy in terms largely of its passive evolution of stars, I would call it by and large a normal galaxy. But there's always some sign of activity. So it's a question of degree that we're talking about. But often what happens is that there's an intense burst of star formation. So these are called starburst galaxies. Either galaxies are colliding and there's a new supply of gas, and there's an intense burst of star formation. The massive stars die off, and they give rise to what are supernovae, the massive stars supernova, and give out a lot of energy and light in electromagnetic radiation, neutrino emission. And this is a very nearby galaxy called M82, Messier 82, and it's a starburst galaxy. And this is a radio image of right in the central region over here. And each of the dots, if you go and image it further, you'll find the remnants of these explosions over here called supernova remnants. So these are also referred to as active galaxies, where the rate of star formation is much more, for example, than what you would find in our own galaxy. What is the value for our own galaxy? It's about a solar mass or two per year. It's the rate at which new stars are forming. In these starburst galaxies, the rate of star formation could be much larger, 100 times larger, sometimes 1,000 times larger. Okay? But it's difficult to sustain this over the lifetime of a galaxy, which is billions of years. So these are episodic activity which keeps going on. But today, since our theme is not on starburst galaxies, but on supermassive black holes, we will focus mostly for the rest of the talk on this category of galaxies called active galactic nuclei, where the energy source is due to the supermassive black hole at the center. Why do we say that is what we will first address. Before that, I'll give you one or two examples of even a small-scale activity, or not the kind of activity we'll talk about in a little while, happening in our own galaxy. For example, what we find when we look at our own galaxy at high energies, which is X-rays and gamma rays, okay? X-rays and gamma rays, then we find that the huge bubbles of highly energetic plasma, which are escaping along the minor axis, perpendicular to the disk of our galaxy, containing a lot of energy as well. And you can see the scales that we're talking about over here, which is in several kiloparsec scale. So these are huge bubbles of plasma going out. There is still a debate whether this is due to the black hole or due to an intense earlier burst of star formation. But a general consensus, or it's approaching sort of, the literature is approaching, where people who work on it, saying that it is possibly due to the black hole. But what we are going to talk about today are phenomena which are far more energetic than that, okay? And these are these active galactic nuclei. I'll give you numbers in a short while, but before I go to the numbers, just to some of the characteristics. So high energy output. For example, the luminosity of our sun is a few times 10 to the power of 33 ergs per second or so. The luminosity of these active galactic nuclei, which I'm talking about, could be 10 to the power of 12, 13, 14 times larger than that. So, 10 to the power of 13 suns, if you put together, that is a kind of luminosity or energy which you have. Sometimes they very often, or often they spew out jets of relativistic plasma. We'll talk about that a little while more. That I showed you the small bubbles, but these are very collimated, highly energetic plasma, which come out from the nucleus of the galaxy, initially traveling at nearly the velocity of light, supplying energy over hundreds of kiloparsecs. 1 parsec, just to remind you, is about 3 light years, 3.26 light years. So we're talking of thousands of light years. And I'll show you some of the images of the largest galaxies which have been mapped today. They're very prominent emission lines. If I look at our own galaxy, the stars have spectra where there are a lot of absorption lines, and if you take a spectrum of the whole galaxy, you'll get a lot of absorption lines. But these AGN, they are governed by very prominent emission lines usually, and they can be very strongly variable as well. This is an illustration of a canonical model of an active galactic nucleus that is currently sort of in vogue. And a broad picture is correct. The details we probably need to work out even more. Right in the center is a supermassive black hole that we talked about in the last few minutes or last 5 or 10 minutes or so. And then there is an accretion disk around the black hole. Why is there an accretion disk? Because when matter is falling into the black hole, it has a certain angular momentum with it. And if it is an angular momentum, it is not going to fall radially inside and be lost to us forever, but it is going to spin around, dissipating energy due to viscous forces. And perpendicular to the direction of this motion, it is going to collapse, whereas along this, centrifugal forces are going to sort of act, and you have a disk structure. And around the disk, there is a donut-shaped structure for which there is a lot of observational evidence, and the jets are moving out in a direction perpendicular to line of sight. Now, this is the canonical model of an active galactic nucleus. I talked about emission lines. The emission lines can be very broad. Broad means that if they're moving about, if these clouds are moving about, the velocities could be thousands of kilometers per second. If you look at our own planetary system, for example, the inner planets like Mercury are moving much faster than the outer planets, Neptune or Uranus. And that is because of the gravitational influence of the sun, right? Where you balance gravity with centrifugal forces going around. So similarly, when you go close to the black hole over here, that you have gas clouds which are moving at thousands of kilometers per second due to the gravitational influence of the black hole. Whereas if you go further away, the lines are going to be narrower. This is going to be an important point that we'll talk about in a short while, and so just bear that in mind. So now let's move on a little bit. And these are just images that I'm trying to show you. This is of a galaxy in the southern hemisphere, imaged by the Meerkat telescope. And I should just mention that I've shared my slides with the organizers. They're happy to share it with anybody, okay? And you can take it from them as well. And this is the galaxy M87, whose black hole we saw, but we also see extended emission on different scales over here. This is about 100 kiloparsec, which is about 300,000 light years. And you can see there's a one-sided jet which is coming out from the nucleus. Whereas on this object on the side, you see a two-sided jet streaming out. These are radio images. The colors are false color images because radio, we don't see color, but these are some of the largest objects that we see. This is the largest one which is being mapped by the LOFAR telescope, which is a European telescope, started with the Netherlands, but telescopes spread across Europe at low frequencies. And this one is about 7 megaparsecs, which means about 20 million light years across. So if you have our galaxy and line up, you have more than 200 of them. You have to line them up to form these largest structures. What is the kind of energies that these kind of objects possess is huge, as I said earlier. I referred to the luminosity, but the energy is huge. And galaxies, like us, they are also occur in groups, they occur in clusters. The galaxies themselves are moving about. And this is one such object which we had imaged with the South African telescope, the Meerkat telescope. This is over again 1 million light years across, but you can see the structures are all sort of complex and bent by the intercluster medium. We try to simulate these with numerical simulations to see how far we can do, and this is a reasonable sort of simulations. What is the energy content is what I'm coming to right now. Is what we're coming to right now. And the total energy is of the order of 10 to the power of 60 ergs or so. And what is the emission process? This is again for physics of students. It is just highly relativistic particles moving in a magnetic field. Used to be referred to as magnetobrainsstrahlung, but nowadays it's the more common term is synchrotron radiation. But basically, very high energy particles moving around in a weak magnetic field, which gives rise to this irradiation which you see in these lobes of emission. This is a very famous radio galaxy called Cygnus A. And if you look at it, the total energy content in these is about 10 to the power of 60 ergs. And what does it mean in 10 to the power of 60 ergs? You can see that The mass of the sun is about 10 to the power of 33 grams or so. Generally, if you look at Einstein's mass to energy conversion, mc squared, the velocity of light is 3 into 10 to the power of 10 roughly. So 50, 33, 43, 53. So it's not just one sun, it's millions of suns. You have to sort of just convert with 100% efficiency in energy to try and account for these energies of these huge loops. So how do you generate that energy? What is the most efficient process by which you can generate this energy? For example, in the sun, energy is generated by nuclear fusion. But that kind of efficiency is completely inadequate to explain this kind of processes that we're talking about. And that's where the supermassive black holes come in. How does it come in? Because if you can convert, because it's a very compact, massive object, if an object falls into it, the potential energy gets converted into kinetic energy, it keeps increasing, and then when it sort of dissipates in a disk, you get the maximum efficiency out of it. It also depends, the efficiency also depends on whether the black hole is stationary or it's a rotating black hole. And the reason is that if it's a rotating black hole, you can get closer to the black hole. The last stable orbit is a bit closer, so you can get more energy out of it. If you look at the efficiency of stellar conversion, it is of nuclear reactions, it's 7 into 10 to the power of minus 3. Whereas if you look at a maximally rotating black hole, it's nearly 40%. Okay? So you can see that because this is the most efficient way of generating energy, and there is evidence for this, but physically we have processes which can extract energy out of these rotating black holes, and that seems to be the most promising way of trying to explain the huge energy output. Then the formation of these jets is a more detailed physics, which we'll not touch upon today, but we'll touch upon a little aspect, which is how fast are these jets moving out? I mentioned earlier that they're moving out at nearly the velocity of light, okay? How do we know that they're moving out at the velocity of light? We have to measure the motion. How do we measure the motion? That if we observe an object with very high angular resolution, not quite the Event Horizon Telescope, which is like a putting an apple on the moon, but say you take a dime or something and put it about 500 to 1,000 kilometers away. So that's the kind of resolution with which would be about a milliarc second or so, that you can try and look at knots of emission like these in the jet. And if you see these knots of emission, you measure them year after year after year after year, and then you say, well, this has moved so much, I know the distance of the object, I know how much it has moved, I know how long I've taken to observe it, distance divided by time is velocity, and I know what the velocity is. But the surprising thing was that when you actually did that exercise, you came out with velocities which are many times the velocity of light. Which sort of, if you first look at it, it's fundamentally inconsistent with special relativity, which says the maximum velocity is that of light. Martin Rees from Cambridge came up initially with a very neat explanation of this. I will just give you a heuristic explanation of it, but as I do that, students who may be a bit more mathematical can look at this figure. But basically, you can get motion which is much larger than the velocity of light. Not physical motion, not physical velocity, not velocity at which information is conveyed, but the velocity which is apparent. Why does it happen? For example, let me say that I emit a plasmon from this pointer over here, and this pointer or the jet is coming towards you. So what happens is this plasmon is traveling upwards, and then let me take another light sort of wave front which is coming out a little later. All right. Now, because this velocity, this plasmon is moving at almost the velocity of light and is coming towards you, you see the two wave fronts are very close to one another. So the actual time which you record is actually squashed. So you get the distance which is projected, but you have an apparent time lapse which is really very small because the wave front is almost keeping up with the plasmon which it is emitting. The two signals get compressed. If the jet is pointing away from you, pointing it in another direction, that's not going to happen. Okay? So when you see apparent motion, which is many times the velocity of light, it can only happen physically if you have emissions or jets of plasma which are coming towards you at a velocity which is very close to that of light. And what also happens when you see these velocities coming close, components coming at high velocities towards you, special relativistic effects, which I'll not deal it in detail over here, they also enhance the apparent flux density of the source. So when you see these one-sided jets, they are because these jets are coming towards you and their flux density is enhanced. There is a jet on the opposite side, but it is much weaker, and because it is much weaker, you do not see it over here. Okay, these are all one-sided jets you can see, even in M87, but you see the extended emission, for example, even in the image of Cygnus A, or this particular image which I'm showing you over here, that these lobes or extended emission are plowing its way through the medium. They are much slower, so you don't see these effects. But on the other hand, for the jets which are coming towards you, you see apparent motion which can be much greater than the velocity of light. Now this, I will introduce you briefly to the kind of active galactic nuclei in terms of the wide spectrum that exists, but I want to point out one very important aspect with this figure over here. The important aspect is that we are not in any special location in the universe. Although I can see objects which exhibit motion which is greater than the velocity of light because the plasmon is coming towards me and is keeping up with the wavefront which it emitted earlier, okay? For example, I mean, if I were to repeat that again, let me say that a wavefront is going out. Sometime later, a little later, this, a plasmon is being emitted. Because the plasmon is keeping up with the wavefront, that the time between these two gets squashed, and when you divide distance by time, you get a high velocity. But we are not in any special location in the universe. The universe doesn't care about us. So objects will have to be randomly distributed in the sky. So if there are objects where we see superluminal motion because the jets are pointing towards us, there will also be many, many objects which are oriented in other directions. And they will look different. They will look different, the nuclear emission would look different because the jets would either be two-sided or they would be very weak. They would not be like the one-sided jets over here. So some of the apparent diversity of these kinds of galaxies are because they're oriented differently towards us compared to the ones which are at larger angles. So this is an important aspect of our understanding of active galactic nuclei with supermassive black holes, which we have to take into account. Some of these objects which we see have broad emission lines, some have narrow emission lines. These are, I've just written down, just to give you a flavor of different kinds of active galactic nuclei which have been identified, depending on the luminosity, depending upon whether the radioluminosity is high or low, and the kind of parent optical galaxies that they're associated with. But let me just dwell upon this point, which I mentioned a little while earlier. This particular figure I'll go back to. I mentioned that near the black hole, the galaxies, the line-emitting gas is moving about much more rapidly. And that is because of the gravitational influence of a supermassive black hole. The further away you go, the velocities will be larger, smaller. Closer to the black hole, velocities will be larger. Similar to our solar system. Same physics over here. So what happens is that there is a torus, donut-shaped torus over here. If I get a direct view of this broad line region, I will see the broad lines. If I get a side view of it, if this torus obstructs my side of view, I'm only going to see the narrow lines. I'm not going to see the broad lines. So these are aspects which have also been folded into in our understanding of active galactic nuclei. This is a galaxy where you can see there are the broad lines over here. This is an object where we are being able to see them directly. So if I look at the next object, I don't see the broad lines at all. This is what is called a Seaford 2 galaxy. I'm seeing it from the side. So our view of the universe of active galactic nuclei depends on relativistic motion and its orientation relative to the line of sight towards you. Okay? Okay. Maybe I've spoken quite a bit. We have about 10 or 11 minutes more. I just have one or two more slides. But do you have any questions that you may have? Yeah. Please. Okay.
Now I can speak. I'm sorry. I just wondered why is wavelength is measured in angstroms.
Why? Sorry, say it again.
The previous slide you shown.
The host galaxies are different.
Yeah, and I wondered why the specifics for that purpose, the wavelength is shown in angstroms and not in like millimeters?
Okay, okay. Let me go back to the previous slide and just try and address that a little bit. Then we'll move on. Okay. This is the slide you're talking about.
No, next one. The next one.
Next one.
Yes, the image that is shown like to the right and.
Okay. Okay. Let me try and explain this a little bit more. Okay. This is the supermassive black hole sitting over here, and these are the broad line emitting clouds, and because they're very close to the black hole, and these are the ones which are further from the black hole. Their emission lines are narrow. So if you were to look at an object from this angle over here, if this is the way you view it, then you will be able to see the broad emission lines, which are optical emission lines, and as well as the narrow lines. If an object is oriented such that I can only see the object from this line of sight, then these broad lines will be blocked from my view by this torus of material around the central black hole, and I will only be able to see the narrow lines over here. So I've also shown over here the typical spectrum that you will see of an ordinary galaxy, which is not an AGN, but this is what is a Seaford galaxy, which is associated with a spiral galaxy. There are issues about why spiral galaxies have less luminous jets compared to elliptical galaxies, but that is something which we are still, it's a matter of debate, but that is something which is a bit too detailed to deal with today. But basically, it is the location of the line-emitting clouds and the way the object is oriented towards you. This is in the optical region of the spectrum, which is 4,000 to 8,000 angstroms. All right?
What is the angstroms measurement unit?
10 to the power minus 8 meters. Angstrom. Is that what you asked? Nano.
Yes, and I wondered about is there chemical elements, right?
Is there
like that spectrum that is shown?
Yeah.
There's the peaks are responding to chemical elements. Yes.
So this is a spectrum which has been taken in the optical region of the spectrum, and these lines are due to species, different elements, where hydrogen, magnesium, calcium. These are the common elements which you see over there. And this is basically where the gases, sort of ionize and then they recombine. So these are the recombination lines of the gaseous clouds which are present in that region. This is basically the optical region of the electromagnetic spectrum.
Okay.
Yeah?
Thank you.
Yeah, optical region of the electromagnetic
I just quickly wondered what is the erg unit for energy?
Erg. The definition of an erg?
Yeah.
Okay. Okay. The definition of an erg, where you apply a force of 1 dyne per centimeter squared and you move an object by one centimeter. So it's a centrigram. It's a basic unit of energy in the CGS unit, which is centimeter gram second.
Okay. Thank you.
Yeah. All right. Now, okay. Now there are just 2 slides more. We'll finish with that, and you can take some more questions till time runs out. Okay. Now this is I've sort of largely dealt with the radio regime, because that is where a lot of these features like jets and the lobes are easily visible, but these active galactic nuclei, where energy is extracted from accretion onto a black hole, they emit across the electromagnetic spectrum, which means from energies which are several meters in length. So the energy, if you calculate, would be about 10 to the power minus 7 electron volts, and then to the highest energies, which would be, tera electron volts or so. So you're talking about 20 orders of magnitude. Now, when the jets are beamed towards you, which you talked about, then these high energy photons also get enhanced. And there is a very famous telescope which is still functioning called the Fermi Gamma Ray Telescope, which has actually contributed immensely to our understanding of the gamma ray sky. And a lot of these objects, don't worry too much about the details, but the bulk of the sources which we have over here are due to these objects where the jets are pointed towards you because their flux density is enhanced. Now, in terms of techniques, you also find that there is a large portion where we don't have any optical objects as well. So what happens is that I talk to you about resolution. I talk to you about how long baselines and short wavelengths will give you angular resolution. But what happens is that in a radio telescope or in an optical telescope, or even if you go to the X-ray telescopes, that you can focus the rays, okay? You can focus the rays, bring it to a point, make a sharp image. But what happens at the highest energies? I mean, X-rays you're familiar with. If you break your bone, they will take an X-ray, photons will go through. But X-rays also, you can try and focus them by having, mirrors at grazing incidence. But with gamma rays, because of the highest energies that are available, that you can't even do that. Whatever you try to focus, it'll just absorb it, the photons will go to it. So your whole telescope is effectively the detector. Radio photons, optical photons, I can reflect it off a mirror or reflect it off an antenna, catch it in a focus. With gamma ray telescopes, I can't do that. The whole telescope detector is effectively a telescope. And what happens is the way you detect it is that these very high energy photons will create pairs of positrons, electrons, which will actually give out radiation, which you try and detect. So the resolution is very poor. So imaging is a bit of a challenge. So these are largely based on detections of gamma rays, and you see that the bulk of them are actually objects which are pointed towards you. But the only reason I wanted to point this slide out or put this slide in is to illustrate to the fact that the kinds of energies which we have been able to generate, or nature is able to generate, to give rise to emission at gamma ray frequencies as well, at the highest energies, is something which you still struggle to do on the Earth in terms of accelerators and all that. So nature appears to be able to accelerate particles to the highest energies to give you photons at the at the tera-electron volts or giga-electron volts, the highest kind of energies that we can get. So we are getting close to it. So I will try and, I thought I should show you one last slide, which is a very recent result again. So we talked about supermassive black holes, about 10 to the power of 6 solar masses to billion solar masses. Now, one of the very outstanding astrophysical questions today is, how do these black holes grow? How do they form? How do you get such massive black holes? For example, if I have a massive star of 20, 30 solar, or even 200 solar mass, I cannot get a million solar mass black hole as a remnant of a massive star. Perhaps in the very early universe, there were even more massive stars which lived very shortly and gave rise to massive black holes. But it is very difficult to generate these supermassive black holes. And the ideas which have been floating around is that these black holes probably in the early universe went through a very rapid process of accretion, of accreting matter onto the stars, or they could have been smaller sized black holes which coalesced together to try and, or combine together to give rise to more and more massive black holes. When black holes combine, they sort of rapidly spin around and become one black hole, and they give rise to gravitational waves. Gravitational waves from intermediate mass black holes or hundreds of solar mass black holes have been detected by the gravitation wave detectors. Now, this is the only example which has been reported again very recently, just last month, led by a German group at the Max Planck Institute, Hanne Ubler, who have found actually in a very distant object, 12.5 billion light years away, when our universe was just 1.2 billion years young, 3 supermassive black holes in a galaxy, and they're not all at the center. So this is sort of one of the only evidences to show that multiple supermassive black holes can also form, and with time they'll probably coalesce to form more massive black holes. But again, we are still here looking at several million solar mass black holes. Now, a question which might come to you is that this is 12.5 billion light years away. That how do you estimate these masses? So this again comes from trying to detect the velocity of gas around these systems. Because once the gas is moving about very rapidly, the lines are going to be broad. And there is no other way that you can generate these broad lines away from a massive object, because this is really Doppler motion of very massive objects. So they have done very careful observations of high resolution to try and get very accurate spectra, looking at the line profiles, looking at how the velocities are moving about to infer the masses of these black holes. So we have a story of at least some telltale evidence that supermassive black holes grow via accretion as well as coalescence, and accretion onto these massive black holes give rise to the kind of jets which you talked about, the whole category of active galactic nuclei, which span a wide range of luminosity and size as well. So I'll end with that, and thank you very much for patiently listening. If there is time, we can take some more questions. I have to catch a bus, but even after this formal thing is over, if some of you are around, 5-10 minutes we can spend just interacting and addressing your questions. All right.
All right, thank you so much. We have a little present from the library.
Thank
And
you. Thank you
if
very much.
somebody has a question, please put their hand up. And we have time for a few more questions if anyone has.
Hey, it's not okay. Is gamma so gamma ray telescopes, should they be like in orbits in order to not have the most of gamma rays blocked by atmosphere?
Excellent question. Okay, okay, that's a very good question. Okay, see, most of the electromagnetic window is actually opaque, as he has pointed out. All right, there are two narrow windows which are open. No, one narrow window which is open, which is the optical with which you can see. And one very interesting aspect of this window is that the sun, radiates at a temperature where the solar radiation also peaks in this window. So, okay, I mean, the atmosphere has evolved in a way that it lets in this window, and our eyes must have biologically evolved to be able to see, so that our eye response is also matched to the spectrum of the radiation from the sun. The other window which is available is a radio window. At very low frequencies, the ionosphere cuts us off. Very low frequency below about 10 megahertz find it difficult to come to the ionosphere. They'll be absorbed. But beyond that, till the millimeter region, it is open. Then in the millimeter wave region, you have to go high on the mountain tops. Water vapor, etc., cuts off radiation depending upon where the transitions are. And the question which he has asked is a gamma ray region. X-rays and gamma rays are completely blocked by our atmosphere. So how do we see it? There are two ways. There are two things, actually. One is to put, as he pointed out, is to have an orbiting telescope outside the Earth's atmosphere, and the Fermi telescope, whose results I showed over here, is an orbiting telescope, which has yielded a wealth of information. But there's another aspect to it. The other aspect to it is that as you go to higher and higher energies, the number of photons, or the number of high energy particles, even cosmic ray particles, get less and less. So the thing is that if you build a spaceborne telescope, which can only be certain limited size, that some of these photons, you may get one photon in 1 square meter over 100 years. So there's no hope of trying to detect them with telescopes in space. For example, when the highest energy particles were detected, about 10 to the power of 21 electron volts, which was detected, is a particle. People shouted out in the lab, "Oh my God!" and the particle came to be known as the "Oh my God" particle. And there are some of these particles there are more of these particles that we have detected. But what do we do to detect the highest energy photons? What do we do? Then we use the atmosphere as a telescope. Because when a high energy photon comes to the atmosphere, the highest energies, they're very few in number, they will actually ionize particles and give rise to a cascade of high energy particles. And then you can build a telescope which will give off light radiation as these high energy particles move through our atmosphere. So you build an array of telescopes spread over several, hundreds of square kilometers could be. Today they give radiation which is called Cherenkov radiation, where the particle is traveling at a velocity which is great, not greater than the absolute velocity of light, but greater than the velocity of light in the medium. They give rise to what is called Cherenkov radiation, which is named after a Russian physicist, and you try and detect that radiation. And today there is a Cherenkov telescope array which is under construction, which will be the best ones available in terms of both localizing as well as sensitivity. One component is in the La Palma Islands, and one component is in Chile. So you're absolutely right. For certain energy ranges where the particle energies are, you'll detect a fair number of photons orbiting, but the highest energy photons you use as ground-based air shower experiments. Yep.
Thank you.
Okay, yeah, I was just wondering, so with LISA, With Lisa eventually, hopefully coming online, is that going to be able to provide more kind of details about the stuff you have on your last slide here, like these
Actually,
reorbiting?
I've shared my slides with them. They're welcome to share it.
Yeah.
My email is also there. So if you want any further information, I'll be happy to sort of respond to it.
Sure. Okay.
Yeah.
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 All right, let's thank Professor Dhruba Saikia again.
Let me take a picture of all of you, Let me just take a picture of all of you. Just 1 minute. You come here.
No.
When do you come?